All right. Good afternoon, everybody. Let's get the link shared here. And then we can begin. There's that post. Yeah. Oh my gosh, we actually have one in person now. Amazing. Okay, do we have Ryan? Don't see, wait. Let's see, we have Emma, we've got Ariel, we've got Giselle, got Carlos and Jasmine and Cynthia and Denver. Okay, everyone is here. Excellent. So before we dive in to the math, let me make a quick note here. Despite what current events may or may not be indicating, okay, I checked this morning, 2 plus 2 is still equal to 4. Triangles still have 3 sides, okay? Math still works. We can still have class. The universe is not broken, okay? And best of all, God is still good. So let that be our driving force moving forward, okay? With that said then, I said forward, but we're actually going to roll back for just a moment to yesterday's work, which was, all confused with the numbers, 2.6, right? Yeah. Here we go, the parallel lines. So please go ahead and take out or open up your parallel lines exercises from yesterday and check your work here. Okay, 1, 2, and 3, fairly straightforward. 4, 5, 6, you're working backwards here. Remember, if parallel lines, then these things are congruent, or if these things are congruent, then the parallel lines, right? So goes in both directions. So you can use that to justify 4 is parallel, 5 is not. 6, though, 6, the only angles they give us is relative to this extra set of lines they threw in there. And we cannot determine this from the conjectures we know right now. But I'm making a note to come back to this later, because I think we can actually determine this. We just need a few more facts and conjectures to work with. But I think it's doable. Okay? And then number 7 there. There's all of the results there. I tried to put them as close as I could. So E here is the 26 degrees and F is the 58 degrees. And then finally 8 and 9. 8 here is 80 degrees, and 9, x is 20 degrees, y is 25 degrees. Okay, any questions from yesterday's exercises? Anything you need me to go back to? See again? Explain. No? All right, then let's move forward. What happens when you put multiple angles and lines and things together? You get polygons. All right? polygons are composed of more angles and lines. And so we're going to investigate and see if we can't, from what we already know about angles and parallel lines, can we extrapolate that further to figure out something about the angles inside polygons? Because this is very handy if, say, you want to like build a hexagonal deck or something. Right? You might want to know what the angles involved are. So what I'm going to do here today is put together most of an argument. It's not a foolproof argument. I'm not proving these things yet. We will come back and do that at a later time. But I want us to at least be able to see some reasoning for these statements and relationships instead of just throwing them at you. Here's the fact, memorize it. Okay? I want you to have some reasonable grounds for knowing this. So, here's what we know so far already. We know that a straight line angle here would be a full 180 degrees. I'm going in one direction and I turn completely around to face the other way, that's 180 degrees. And then inside parallel lines, we found that any combination of an acute and an obtuse angle would also be summed to 180 degrees. They are supplementary. And so there's another specific set, another pairing, just like alternate interior and all those. We could talk about the consecutive interior angles, and that's what these two guys represent. Right, so between the two parallel lines, on the same side as the transversal here, you could have two consecutive interior angles, or CIA for short. You might see that abbreviation in the future. And those will always be supplementary if the lines are parallel. So keep that in mind. That's another specific case of parallel line relationships. So what can we deduce from there? Well, the first thing we can do is I've got to adjust those. So I'm going to switch to here. Aha! You can't see what I'm doing? I need to erase last period's stuff. I forgot to do that. I don't want to spoil it and give it all away. But think about this. What happens if I had two sets of parallel lines? That is to say, 4 lines all together. What would we end up with? What kind of a shape is that? We've defined this already, right? A parallelogram, right? Quadrilateral, both opposite sides are parallel to each other. So if you treat this as, hey, between these two parallel lines, I have a consecutive interior angle relationship. So let's use green here, right? These two angles make 180 degrees. And then on this side, I have another pair of consecutive interior angles between these two parallel lines. So then these two will add to 180 degrees, right? So then what is the sum total of this angle plus this angle plus this angle plus this angle? All 4 interior angles of the parallelogram adds up to what? I've got the speaker on. Go ahead and shout it out. 2 pairs of 180. 2 pairs of 180. Multiply by 2, not divide. Yes. 180 times 2 is? Anybody? We already talked about this with the circles. What was that? 360. Yes, 360 degrees to go all the way around, right? Okay. 90, 180, 360. Some of our favorite numbers in geometry. You're going to have to learn to love those and how they relate to one another, okay? Double and half, 180, all the time. We're going to be using those 4 numbers a lot. So that's pretty well proven, actually. We could write that out and make a formal proof there to say, based on this relationship of parallel lines, I can show that the sum of the angles inside a parallelogram must be 360 degrees. But that's not generalized. We can't generalize that very well. Right? Not every shape is a parallelogram. But if we take that parallelogram and we cut it in half, we would get 2 triangles. Let me get another highlighter here. And those 2 triangles then still have the same sum of their interior angles. So the 3 green angles plus the 3 orange angles. Notice here that we've got a pair of green and orange that create those original red angles from the parallelogram. So I haven't added any new angles. I haven't taken anything away. All of the same degrees are all still there. Okay, we haven't changed that. I've just divided this one into 2 separate pieces. Okay? But however I've divided this one, I've also divided that one the same, right? So if you think this is got the smaller half, then I took the bigger half over here, so it balances out. Okay? So can we safely agree that this should be exactly half of those 360 degrees? So now we're back down to 180. So this is not a proof, but it is at least a reasonable assumption, right, that a triangle should have an interior sum of 180 degrees. And in fact, we are going to say that the sum of the interior angles of any triangle is 180 degrees. And we call that the Triangle Sum Conjecture. It's as if it's important or something. Need a freeze button. I don't think I... No? Okay. Now, I didn't prove that because I said any. And at this point, you should be thinking, any triangle? Really? That sounds awfully suspicious. Like you can just take this and generalize it to whatever triangle, anytime? It always works out? That seems rather unreasonable. And it absolutely does sound completely unreasonable that it should always work out, but it does. And we will spend more time on Friday investigating that and come to a much better proof and certainty that, yes, this is definitely the case. We can rely on this as a triangle sum theorem, okay? Better than a conjecture. But for now, I'm asking that you accept that because we're going to build on top of that. Because triangles are everywhere. And if we know the interior sum of the triangle, we can figure out the interior angle sums of any object made out of triangles, which is all of them. Everything can be made up of triangles. In fact, any video game ever, at least any 3D graphics at least, everything is made out of triangles. Okay? Even Minecraft. I know it looks like everything is made up of cubes, but each cube is actually, the squares are all made out of 2 triangles, similar to this idea up here. Okay? So yes, you can literally represent anything as multiple triangles pieced together, which leads us to these other polygons. I've already got them drawn in. I apologize. Don't look too closely. But take a look. We've already got the rectangle there. okay? We've seen that just like the parallelogram. We can divide it in half, and you've got 180 degrees from here, 180 degrees from here, so you add them together. And so the interior sum for any quadrilateral, because no matter how I distort it and shape it, I can cut it into two triangles, will always be twice that, 360. Look at the pentagon, okay? 5 sides, and I can divide it now into 3 triangles. Or we could divide it another way, right? You could do from this side. And what about that side? Well, now I've got 1, 2, 3 triangles and a quadrilateral. Okay, what if I like cut this one? We can't do that. Okay? You haven't cleanly divided it because you've added now angles here that weren't there before. The only thing you're allowed to do is divide up the existing angles. So only these angles get to be subdivided with another line running through them. All right? Which in the case of the pentagon means you're drawing 2 diagonals from the same vertex. There's not a whole lot of possibilities there. So you get 3 triangles. Take a look at the hexagon here. The hexagon now, I get 4 triangles, and there's lots of different ways to do that. This very irregular guy, this isn't even a convex polygon. It's concave. Look at this dent in the side here. But you can still do it. You can draw all of them from here. You can draw all of them from here. You get a very skinny triangle here in the middle, but it would still work. Okay? There's lots of ways to carve this up. Let me make that a little bit cleaner. Okay. Now, I have only connected vertices with diagonals of the polygon. I have only subdivided existing angles, and I've divided, this is a triangle, this is a triangle, this is a triangle, this is a triangle. There's no space left that is not a triangle. So you will always be able to get 4 triangles out of a hexagon. So, one more time. I don't spoil it for you. I'm going to clear that. Go ahead and create a little table then of our results here. For any given amount of sides, we can determine how many degrees inside of it. What is the interior angle sum? And then from that sum, if you're making a regular shape, as I say, you're making all of the angles congruent to each other, you can find out what the measure would be. So if you wanted to build a pentagon, a perfectly congruent regular pentagon, like, say, the one in Washington, D.C., right? Or you want to make a hexagonal deck in the backyard, you need to know what that angle is going to be when you put it together. We can use this to help find out. So let's see if we can't find the general pattern here. We know that 4 sides divides into 2 triangles, gives us a sum of 360 degrees. And so we can take that 360 degrees and divide it evenly into all 4 corners, and you get a 90-degree angle measure. What about for 5 sides? We've shown that will always divide into 3 triangles. And so 3 triangles, each 180 degrees, we now have a grand total of how many? What is 3 times 180? Ooh, Ariel's got it. 540, thank you. 540 degrees. And next up, take 540. If you divide that into all 5 corners, you get what? 540 divided by 5. It's at least 100. I know Ariel's not the only one with a calculator. $540 divided by 5. $108. Thank you, Ariel. 108 degrees per angle. All right, we're going to keep going. You guys better pick up the pace. We'll be here all day. 6 sides, 4 triangles. Notice that this is twice as many as 2 triangles. So 360 times 2, or 180 times 4, gives us a grand total of 'I need more than just Ariel to be doing these. This is how I know you haven't fallen asleep on me. Thank you, Giselle. 720. That wasn't so bad. All right, and then if you take 720 and divide it 6 ways, you get $120. Thank you. All right, last one. I think we're seeing the pattern here, right? Sides go up 4, 5, 6. Number of triangles, 2, 3, 4. So if I jump to 8 sides, how many triangles do we expect to have? 6, right? So to find the sum, I'm going to take 6 times 360, and we're going to get 6 Ariel. I jumped up 2 extra sides. I skipped 7. Know this one? It's a big one. 360 times 6. Yeah, 2,160 degrees now. And now divide that by 8. 270, he says. Wow, that's a lot. Right? That's huge. I think. So what's the general pattern there? What would you say about the number of triangles for any given n-sided polygon? If it was 4, it was 2. If we had 5, it's down to 3. 6, 4, 8, 6. Whatever n you have, the number of triangles you can draw is always 2 less, right? So then the sum is always going to be that number times 180 degrees. Put a box around that. That's a good formula to know. That can save you a lot of time. I don't recommend trying to memorize this whole list. Numbers here. Just know the formula there. You can jump straight to it. And if you don't remember the formula, at least remember these 2 facts. You can always divide any shape up into triangles. And every triangle has an interior sum of 180 degrees. That'll let you figure it out for anything, okay? Even if it's some crazy combination of polygons stuck together. And then, of course, if you're dealing with just a regular polygon, you can take that formula and divide by the number of sides again to get the regular angle measurement. So you could use that for whatever deck building purposes you may need. Okay, any questions on those? No? Okay. Then we have one more thing to add, and that is the exterior angles. We've been talking about all the inside angles. What about if you wanted to go outside of the polygon? That's totally allowed, but we got to be very careful with how we do it. So I have drawn here a pentagon with some exterior angles included here. What I've done is I've extended the sides. So instead of just the line segment enough to make the side, I've extended it into a full line, or a ray in some case. So you can see the line goes beyond the bounds of the shape. This line extends past where the next one is. And so what we can do with that is we can look at an angle, right, that's on the outside. Here's the inside. All the red ones are inside the pentagon, and all the blue ones are outside the pentagon. But notice here, if I extend both sides, I get 1, 2, 3 separate angles outside the pentagon. And out here, I've got this angle, and we could even count this as an angle. That's a straight 180-degree angle. Do you count that as well? And the answer is no, not quite. We're only going to be working with all of them in a single direction. All the clockwise angles or all the counterclockwise angles. What you want to create is a pinwheel effect. If you kind of just look at this half, right? Ignore this one because I have that extra bit there. Right? You've got kind of a pinwheel effect here where each side is extending out in the same relative direction. Each angle is on the clockwise side of the pentagon. And when you do that, when you focus your exterior angle analysis to just those types of angles. You can think of this in terms of making a rotation. That's essentially what an angle is. It's a rotate from this direction to that direction. So imagine, if you will, you go for a walk outside. You leave your house, you go to the corner of the block, you're facing this direction, you go, I'm going to walk around my block. So you turn down the street and you start walking. And you get to the next intersection, and you could go either way you want, but you're going to stick with one direction each time because you didn't make it around the block. You don't want to walk around the whole neighborhood. So you turn from facing this direction, turn now to facing that direction. So you turn through this angle, and now you go this way. And then you were facing this way, direction, and when you get to the next intersection, you turn again, and now you walk this way. Next intersection, turn again, this way, intersection, turn. Now you're back to facing the direction you started in. So the question is, if I add up all of those blue arcs, those clockwise exterior angles, what is the total turned? Ooh, Giselle's got a good answer. Anyone else? Think of it this way. It doesn't really matter how long I've walked. The size of the block makes no difference. It's about the total turning. So I could do the same thing in my chair. Right? I could go that way. Okay, walk the block. Turn to the next road. Walk the block. Turn to the next road. Walk the block. Turn to the next road. I'm back where I started. How many degrees did I just rotate? What's that? 360, right? I've gone all the way around in a circle. And in fact, that's what's going to happen every time, no matter how many roads or intersections are there, no matter what type of polygon it is, regular or irregular. It does have to be convex, though. We will consider that. But it will always be 360 degrees. So here's another picture. As you're writing that down, think about this. What if I take that polygon and I shrink it? Here's what they're doing there. The polygon, the pentagon in the middle is getting smaller and smaller, but they're still extending those sides all the way out until you get all the way down to the bottom where the whole polygon fits at a single point. It's merged together, and then each of those exterior angles now is just a rotation about that point. And so you have now just the full circle all the way around, 360. Okay. So now you know the angles inside a polygon, the angles outside a polygon. You can use that to answer questions now that involve more than just parallel lines and triangles. You could find the angles inside just about anything. Pretty sure exactly anything, because whatever it is, assuming we're talking straight sides here. Right? We haven't gotten into the realm of curves and arcs of circles yet. But for our exercises today, we're now dealing with these kinds of shapes where we got funny looking pentagons in here. 1, 2, 3, 4, 5. That's 5 sides, 5 shapes. So you know what these all have to add up to be, right? We know how D relates to the 97. That's a linear pair there. We've got a triangle out here. We know what those have to add up to be. It's telling us, hey, this is an isosceles triangle. These are congruent, so we've got some symmetry to exploit there. Okay, use that to your advantage, and you should be able to find the rest. Oh, and these are parallel lines. Oh, all kinds of good given information here. Okay, so use each of those in turn to fill those out. Same with down here. Number 6 is probably one of the trickier ones. We've got a whole bunch of regular shapes. Right? Same size sides, same angles all the way around. So you can use that. Go ahead and find the sum. We found out what this angle should be for a regular pentagon. Use that. And then notice here, all of these angles, this angle in the pentagon, the square, and the triangle, plus angle A, 1, 2, 3, all 4 of them together combine to form a full circle around this point. So you can use that, add those 3 up, subtract from 360 to find A. All right? It seems rather straightforward, but many people end up forgetting that one. All right, we've got, looks like 8 minutes or so left to work. Any questions before I let you go? No? All right, then you have the rest of the period to work. Go for it. I'll leave you to it.